Drawing a cyclohexane ring is not very hard if you just follow these few steps. You draw two parallel lines as if they were in a parallelogram. After you do that, you put a point above the two lowest carbons and on the same level as the other carbons. So I pick these two lowest carbons and I put a point up here, and notice this is at the same level as this carbon. Next, I put another point down here that is lower than those two high carbons and about at the same level as this. And then I connect the lines. The cyclohexane ring is the most stable ring that there is when it's in the chair conformation. But to go from one chair to flip to the other chair, you have to go through some strained configurations. And the strained configuration that we have is the twist boat cyclohexane. It has strain because there's torsional strain, and to go to the twist boat, you actually have to have eclipsed hydrogens in that temporary state when you twist from the chair into the twist boat or boat. This is not a resting conformation. It's not stable this way. The chair is the most stable conformation, but to go from one chair to a flipped chair, this is not turning the whole molecule over, but flipping one flap on the end up to the other flap on the end down. And when you flip the chair conformation, it has to go through this high energy state. It doesn't really rest there. It only rests in the chair conformation. All right, when you have the chair conformation, there are 6 carbons that are going to be in what we call the equatorial position and 6 that are going to be in what we call axial configuration. 6 axial up and 6 axial down. Now, if you go ahead and look at these on the outside that look kind of like a tutu on the ring, those are called the equatorial position because they're on the equator. The ones that are called axial are the ones that stick up if you were to have an axis right through here about which you could twirl this around and around like a tutu, like a ballerina with a tutu. These right here are parallel to the axis, and so they're called axial. The axial positions have some strain. Why? Because there's a little bit of torsional strain, not a lot. They're pretty far away from each other. But the equator, and they have less space here, we'll see. For hydrogen, it doesn't matter because it's so tiny. But when you get a group that is bigger than a hydrogen, then it starts feeling a group over here, and we'll show you that in a little bit. These equatorial positions, though, have a huge amount of space around them. So they tend to be roomier, and big groups go there. Now, notice when we are in the chair conformation, all the carbon-hydrogen bonds and even the carbon-carbon bonds in the ring are now staggered. So this is low energy. Okay, this is showing you how you can take the cyclohexane ring and draw in axial bonds. Up here, these are all axial, and so you just draw them going straight up or straight down. Make sure that if this is high, notice this is high compared to this position, that the high have the axial going up and the low have the axial going down. If we're looking at the equatorial positions, they are actually going out from the carbons. And so in these two positions, they go out this way. In this position, out is back this way. And the way that we figure out which direction they're pointing is we think tetrahedral. So this carbon is tetrahedral. There is a hydrogen pointing up. And so for the tetrahedral position to be adhered to, it has to come back this way. Likewise here, there's a hydrogen pointing down. And so this position has to be coming away from the ring in a tetrahedral position. And then the other equatorials are on the end carbons, the flaps. Those are very easy to draw just going outward. Notice there's a hydrogen that would be pointing up here, and here is the axial position. There's a hydrogen that would be pointing down here, and this is the axial position. So this is what all the positions look like on a completed cyclohexane. As I told you, the chair can flip. Notice what's happening here is that this carbon actually flaps downward. You see, it is down over here now. And then this carbon flaps upward, and you see it is up over here. And so it actually very quickly flips back and forth, especially if there's no large groups on the ring to interfere with the flipping procedure. When you have a ring flip, the equatorial positions now become axial, and the axial positions now become equatorial. And that's how you always have in every ring, every cyclohexane ring, there's a flip. The axial become equatorial and the equatorial become axial. Notice the axial pointing up are on alternating carbons. The axial pointing down are on alternating carbons. Of course, equatorial are on each one, and they're all out. Something else I want you to notice about these positions, and that is, if we're considering this ring to be flat, if we were to flatten it out so that these carbon bonds right here were all in the same plane, we would call this up and that down. Do you see how this is above this one? So we call this position up. We also call this position up. Why? Because this position is down. If I look at this chair conformation, notice the up position is an axial here. The next one, the up position is equatorial. The next one, the up position is axial. Next one, up position is equatorial. And it goes that same with the down. So keep that in mind when you're trying to visualize these rings. Because the equatorial position has more room, that position is more stable for a group to be in. So when you have something like a methyl group on the cyclohexane, methyl cyclohexane, the methyl group is going to force the ring to stay a little bit longer in the position that puts it in an equatorial position. It will go to an axial position because the ring will flip. Unless you have it incredibly cold, you're going to have the ring flip. But it's going to reside a little longer in that conformation that gives it the equatorial position. The bigger the group, the more it's going to want to stay in that equatorial position. Okay, now if you look at this axial position, this group is actually kind of big, like this. It has space. Those carbons, the hydrogens stick out from the carbon a good way, and they're going to be having a steric interaction with that. What does steric strain mean again? Steric strain means you have the atoms kind of bumping into each other, or at least their electron fields are bumping into each other. The bigger the group, the greater the steric strain here. So this methyl group is going to want to go to this equatorial position, and the compound will stay in this position longer than it'll stay here. It still flips back and forth, but it spends more time in this position. There's a T-butyl group that we could put on here. A T-butyl group is a carbon with 3 carbons attached, and to each of those 3 carbons are 3 hydrogens. So it's a very big group. It actually is big like this. And it resides in this equatorial position even more because it's bigger. So here's an example. This actually is the T-butyl group right down there that I was describing to you. Do you see that the bigger the group, the more there is in steric strain from the 1 to 3 position? We call that a diaxial strain, or steric strain. It's fine. This has a lot of steric strain. Whereas if you put a tiny little fluorine in there, there's very little steric strain. So the bigger the group, the more it wants to stay in that equatorial position. But even a methyl group has some steric strain. All right, cyclohexane can be drawn as a Newman projection. If you go over here and look at this butane in a Newman projection, remember, how do we count this? Carbon 1, carbon 2 in front, carbon 3 is behind and you can't see it, and then carbon 4. This is the least stable, well, the second to least stable conformation, but comparing gauche to anti, this is less stable. Why? Because the carbon and the carbon have gauche interactions. I can go and draw a cyclohexane ring in the same kind of conformation, same projection, Newman projection. Let's count the carbons to look at it. 1, behind is 2, 3, behind is 4, 5 in front, and then 6. So you can see there's 6 carbons. If I look, this carbon is having a gauche interaction with this one, so there's some steric strain there. If I flip the ring, so I've flipped the ring, so now the methyl is rotated slightly, but now the methyl is in the equatorial position. When I put a methyl in the equatorial position, now you see there's no gauche interaction, and so it is more stable. Okay, let's look at disubstituted cyclohexane. Now, in a ring, a cyclohexane ring or any ring, when you have 2 substituents, you have the possibility of being cis or trans. Let's look and see what this one is. If you look, there's a methyl group that's equatorial, but there's an axial hydrogen. That makes this methyl up because it's above the other position of axial. If I look at this carbon, this methyl is up because there is a hydrogen that is equatorial here and down. So this is cis. You can see the cis here too because carbon is up and there is a hydrogen that's down. Carbon is up, there is a hydrogen that's down. So these 2 structures are the same molecule, 1,2 dimethyl hexane, cyclohexane, but it's cis 1,2 dimethyl hexane. If I go ahead and look at this carbon on this methyl, this methyl on this carbon, you can see there's a gauche interaction with this methyl, so that's some steric interaction. There's 1,3 diaxial interaction between this methyl and those 2 hydrogens, so you have a steric strain there. If I look at this structure, this is the ring flip of this. When I flip the ring, remember the axial becomes equatorial and the equatorial becomes axial. Now this axial methyl has 1,3 diaxial strain, but it also is gauche to this methyl, and so there is steric strain there. Flipping the ring does not relieve any strain here. However, if I look at the 1,2 trans, how is this 1,2 trans? If I look at this carbon, there's an axial position and an equatorial position. The methyl's in the equatorial position, up. If I look at this carbon, there is an axial position and an equatorial position, and the methyl is in the equatorial position. If I look at this position, the methyl and the methyl are gauche to each other, so there's steric strain, and gauche interactions are pretty large. Here I have methyl 1,3 diaxial interference with this methyl group here that is axial, and those 2 hydrogens. Here we have the same thing, but there's twice as many. So the difference between this and this is lower energy because you only have that one gauche interaction. Here you've got 2 sets of 1,3 diaxial interactions, so it's higher energy. So on the ring flip that takes equatorial methyl to axial methyl and equatorial methyl to axial methyl, which you find is higher energy. So this would be the preferred conformation over this one. You have the same thing happen when you have 1,3 disubstitution and 1,4 disubstitution. Cis is going to have a different energy than trans. And you go ahead and you look and you see, you figure out what are the interactions in each structure, and then you will be able to find out that actually trans is lower energy for 1,3. Cis is higher energy because there's more axial interactions. If I look at 1,4 substitution, it's the opposite. Cis gives you 1 axial interaction. Trans gives you 2 axial interactions. Every time you go to figure this out, don't memorize which one is going to work. What you need to do is learn how to draw out the structure and think about what kind of strain you have and which structure would be the lowest energy. And the rule of thumb that you always have here is that equatorial positions are always lower in energy. And so if you can get a particular conformation that gives more equatorial positions or gives equatorial positions to the larger group, then that's going to be lower in energy. So now you go ahead and try this problem. Which of the following are going to be the most stable conformation of trans 1-methyl-4-T-butyl cyclohexane? So pick one of these. If I look, the most stable is going to be when both of them are equatorial. How could I find out that they were both equatorial? I could find out they were both equatorial because when they're cis, one has to be axial, one has to be equatorial. But when 1,4 is trans, you can put both in the equatorial position, or both is going to be in the axial position. So you choose the one in which both groups are equatorial. Go ahead and try this one for yourself. Okay, which is the most stable conformation of cis 1-methyl-4-T-butyl cyclohexane? If I look at this, I can either have both groups one group axial and one group equatorial. So I'm going to choose the one that would put the bigger group in the equatorial position. So this right here is the one that is more stable.